Hi guys, today we're going to be going over lab 4 oscillations. So the purpose of this lab was basically to record the motion of a mass attached to a spring and then attempt to model that motion by creating a computational model. And then for this lab I applied the momentum principle, the definition of average velocity, and then the formulas for the various gravitational and spring forces as well as their respective energies. And the main result that I got was that the computational model pretty much resembles the observed model of observed motion, but there are some discrepancies. So now, more in depth about the models I use. So first I use a momentum principle, which is, the definition is just right here, and then the formula is right here, and then using that I derive the velocity update formula, which is shown right here. And then I used the definition of average velocity as well as this formula to derive the position update formula right here. I also used, I'm also going to use the formulas for gravitation and spring force, which is just mg for gravity and then negative ks for the spring force. I also will use the various equations for energy, such as UG equals mgh, spring potential equals 1/2 ks squared, and kinetic energy equals 1/2 mv squared. So now, more into the lab. The system and surroundings of this lab were basically just the spring, the mass, and the earth. Some initial conditions were that the initial position of the mass was at 0.0565 in the x direction and negative 0.423 meters in the y direction, with an initial velocity of 0, a mass of 0.1 kilograms, a spring constant of 6.765, and a initial length of 0.108 meters. And so this for this lab, some more like info about it is that I basically just hooked the mass onto the spring and then released it so that the mass would move in 2D space. So now into the code. This section of code is just basically declaring my initial conditions, such as ball.m equals 0.1, etc. This section of code, I found what the length of the spring was, which is just the position of the mass minus the spring position. And then I found what L hat was, which is just the L vector divided by the magnitude of the L vector, as well as what S is, which is just the magnitude of L vector minus L initial. Since I found the formulas for the energies earlier, I just converted that into code and found what K, UG, and US is. And then the total energy is just the kinetic energy plus gravitational potential plus spring potential. And then for the loop, right here, it's basically the same thing, but delta K is just the new K minus the initial K. Same thing for changing gravitational potential, which is just UG minus UGI. Same thing for delta US, and same thing for delta E. And then I also found the force of gravity, which is just negative m times g in the y direction, so that's why it's a vector, as well as the spring force, which is negative ks times s times L hat, as well as the net force, which is just the force of gravity plus the force of the spring. And then I also declared my velocity and position update formulas right here. So this is my graph for the x position versus time, as well as the y position versus time. And as you can see, there are some discrepancies, and I think these can be like accounted for because of errors in measurement. And then when I recorded my video for the spring, there was some movement in the z direction, and the mass rotated like around the spring. So I think that could account for some of the differences in the oscillations versus the expected. So for the what does it mean question, is the energy principle satisfied? It is, because delta E is 0, which is just this orange line, and this makes sense since no work was done on the system. And then to find the period of oscillation, I found that in the x direction right here, 6 oscillations last around 7 seconds, and so that's the oscillation period for X, and then I do the same thing for Y. And then the difference in oscillation time, which is pretty big, around 0.3 seconds, could be due to, like I said earlier, the rotation of the mass around the spring, things like drag and air resistance, and how each of these things can affect the X and Y components of the motion differently.